Hi, I'm Josh Keegan and welcome to the Space Down Under. And welcome to this interesting live stream about the James Webb Space Telescope. This is the second time I'll be talking about this, as now safely arrived at L2. During this live stream, I'll be joined once again by Aritra Mondal, who will be able to provide some additional comments on JWST and what we will be able to see. So now's the time to grab a cup of coffee, or at least your favorite beverage, get comfy, and let's get started. This evening I am joined by Aritra Mondal, live from India. And Aritra, welcome, Aritra. I hope you're still there. You don't seem to have your screen on. Hello. Hey, yay! Oh, nice background. Love it a lot. Hang on, sorry, just let me correct some stuff here. Whoop. And yes, there we go. That's much better. All right, just to let everybody know and to give everybody a little bit of an idea, Aritra is aspiring to work in astrophysics and is really quite obsessed with the stellar astrophysics and possesses a special interest in rocket science. All of this obsession is started by watching launches on TV and on YouTube, because where else? And of course, like everyone else, is gazing up towards the stars. Welcome, Aritra. Thanks very much for joining me again on the Space Down Under Live to talk about one of my favorite topics, which is the James Webb Space Telescope.
Thank you. And I promise this is going to be good. Better than the last time.
Let's hope so. Let's hope there's no echo and all that sort of stuff. So, hi, Mark. Thanks very much for joining me again, mate. It's good to see you online. Thanks very much for coming back again. So, just a special tribute to Mark Stevens, who's sitting out there as well, who's made some comments. Yes, there is, there will be some stuff again where you will actually be able to add into the chat. Normally the chat box is there. I don't know what's happened to it. But anyway, so yes, the chat box is there. The questions will be answered more towards the end. So please ask as many questions as you possibly can. I have tried to learn as much as I can about the James Webb Space Telescope. I'm not an expert, I'll admit that, and I'll be the first person to admit that, and actually say to you that I don't know. I've basically looked up everything online like I did last time, and it's very interesting deep dive into the James Webb Space Telescope. So just for everyone's reference, the James Webb Space Telescope was launched on the 25th of December 2021, and it finally launched after years of delays and obviously cost overruns. The launch was celebrated by astronomers worldwide as this marked the beginning of a new era and understanding the birth of the universe. So we'll just take a look at that clip that happened on the 25th of December.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And
Allumage
liftoff.
EAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
Trajectoire est nominale.
Vehicle performance is nominal.
Try that again. Now, that was a live location. That's the JWST that actually took off on the 25th of December, launched by ESA, so the European Space Agency, on Ariane 5. Just to let everyone know what had happened with that one, it made it all the way to orbit quite successfully, and it was a nominal orbital trajectory. Since that time, in the corresponding months, the James Webb Space Telescope has actually successfully made it to L2, and as you can see from that screen there that's up that's on there now, is it's actually a live feed of exactly where the James Webb Space Telescope currently is. For everyone who wants to know and understand where it's up to, the James Webb L2 point. Try that again. I got myself tongue-tied. Well done. All right, so to let everyone know, the L2 point, so that's Lagrange 2 point, lies on the through the two large masses beyond the smaller of the two. So it's between the smaller two masses being Earth and Jupiter. So here the gravitational forces of the two large masses balance at the centrifugal force on the body at L2. So what this means is it actually enters into the opposite side of the Earth from the Sun, and the orbital period would be of an object would normally be that greater than of the Earth. The extra pull of the Earth's gravity decreases the orbital period of the object, and at the L2 point, that orbital period becomes equal to Earth. So, like L1, L2 is about 1.5 million kilometers, or 0.01 of an AU from Earth. So we're going to skip right on to the successful deployment of the telescope. So, during this, there's a Northrop Grumman have uploaded a animation of exactly what happened during the intervening months since Aritra and I last spoke. And what would happen during this was the telescope was successfully deployed. So the JWST had 344 identified potential single points of failure during its transition into L2. The JWST had suffered from a number of issues during its development history, including budget overruns, poor management, and blowing out of its original cost estimate from US approximately $500 million to well over $10 billion. So there were also scheduled delays due to hardware mishaps. The cables that actually pulled the sun shield into place had too much slack, leading it to a snagging hazard, and several small tears forming within the shield's 5 independent membranes. The two largest were the 4 inches or the 10 or at least 10 centimeters across. So during this delays and cost overruns and everything, several thousand scientists, engineers, and technicians spanning over 15 countries have contributed to JWST. A total of 258 companies, government agencies, and academic institutions are participating in the project. 142 from the United States, 104 from the 12 European countries, and 12 from Canada. That was
Fantastic animation.
yeah, that was beautiful. Sorry, that animation went on a little bit too long, but that was just beautiful. Other things I need to note as well is that the Ariana 5, Ariane, not Ariana, Ariana Grande. Anyway, no, sorry, the Ariane 5 actually did such a perfect job that it was nominal right down the line. So what that means is it did a perfect orbital insertion. It did right down the line. It was exactly on the green line that they were looking for. The rocket did such a high performance job of placing the James Webb Space Telescope through its initial launch out of the gravity well that it has put it in. It has saved so much fuel that they're thinking now that that it could potentially last 20 years. That's at a stretch, but it's well and truly on its way to actually lasting a full decade. They have saved themselves so much fuel because they didn't need to do course corrections. The course corrections that they needed to do were very minimal. So in terms of actually saving a lot of fuel, this is what the James Webb Space Telescope the Ariane 5 rocket built by the European Space Agency has managed to save for the James Webb Space Telescope. So that just makes me super happy. I'm very, very proud that this could be going, NASA engineers being what they are, could be going for the next 20 years. Just to let you guys know as well, this has happened within the last 24 hours or so. So some images have already come back from James Webb, so the JWST, and what you're looking at here is a selfie. Just believe it or not, the JWST is the first image received, and it's actually a selfie of itself. To align all the 18 mirror segments, the JWST is pointed at HD 84406. And what this has also done is it's also led to its first image. Because it's pointed at HD 84406, it's actually a known point in space and a known star that they can actually start to align the telescope mirrors in with each other. So what appears to be 18 randomly organized dots of starlight is actually the unaligned mirror segments reflecting the light back from the same star back at the Webb's secondary mirror into the near cam detectors, which is exactly how it managed to take the selfie, by the way. It used the near cam detector to actually look at its own mirrors and found out that the previous image that you saw there, which I'll go back one, that bright image is actually pointed directly at the star. So that's that bright image there you can see on that one. So in terms of those 18 bright points of light, so what will happen is in the next coming months, this will all become one image as the mirrors are all aligned. So what they've done is they've identified which dots belong to which particular mirror, mirrors, because there are 18 of them. Some are on the wings, some are in the fore, some are aft. So what they're going to be doing over the coming months is aligning all of those into one single image. Have you seen any of this yet, Aritra?
Yeah, I mean, I was going through these pictures a few hours ago. It blows my mind in one way that this is a very long and a slow process indeed. It has to be what I saw on Wikipedia. It has to be the accuracy has to be around 50 nanometers.
Yes.
So
Yes.
it will take a long time, and as you can see, there are 18 different images of the same star. As you mentioned, HD 84406.
Yep.
So these are the pictures taken separately by each of the 18 minutes. So
Yep.
in a few months' time, what we're gonna see is it means all the 18 images will superimpose to form a single image.
Yeah, exactly. And so when they actually get to that, so the other thing was too is they took a series of images. There was a back video that I was going to add to this live stream, but it was just getting too long at that particular point. What they've actually done is they've identified all the images. They took a particular set of images over a series of time, and what they found was over the set that they had taken, because they expected it to be over a large area, they were quite surprised to actually find it all grouped into one particular smaller region. So that way the mirrors are almost aligned as it is, and they're very close, so they don't have to do major adjustments and all that sort of stuff to the actual mirrors themselves. And there doesn't seem to be any distortions or any loss of quality or anything like that. They're getting exactly what they're looking for. So Mark has also said that, just to take a quick question, even though it's not on screen, Mark has said even though Webb has been delayed so much, it actually will achieve more science because of those delays. So it's actually a good thing. Yeah, Mark, absolutely. Yes, it's a good thing. Don't get me wrong. Look, everyone at the time, and over the last decade of delays and all that sort of stuff, have always criticised the cost and the overruns and all that sort of stuff. But in the long term, anywhere up to 20 years at the avid overestimation of real good science, mate. I got to get into the next part because I could just talk about this all the time. So yeah, I'll just keep pressing on because yeah, it's just going to really give us a very good idea of exactly what the universe looks like. So just getting into it for everybody's knowledge and to let everyone know, the JWST was actually primarily designed for near infrared astronomy, but it also can see orange and red visible light as well as the mid infrared spectrum. Depending on the particular instrument that's pointed at the star. So the design emphasizes the near to mid infrared for three main reasons. The high redshift objects have their visible emissions shifted into the infrared. Colder objects such as debris disks and planets emit most strongly in the infrared, and this band is difficult to study from the ground by existing telescopes such as Hubble. All right, let's have a look at the mirrors. The JWST has a mass of about half of Hubble's telescope, but its primary mass about half double Hubble's telescope, but its primary mirror is a 6.5 meter or 21-foot diameter gold-coated beryllium reflector. Collecting an area over 6 times as large, so 24.5 square meters or 273 square feet, using 18 hexagonal mirrors with a 0.092 square meters or 9.7 square feet obscuration for the secondary support structs. So that's this one here. So yeah, this thing is quite large. When you put a human next to it, you can actually see exactly how large the JWST is. Now, before Aritra gets into his particular presentation, he's going to be doing a presentation at his in a minute, and basically just to let everyone know that the JWST is going to be making observations in the infrared spectrum, and it must be kept under 50 Kelvin. So that's minus 223.2 degrees Celsius or minus 369.7 degrees Fahrenheit. Otherwise, infrared radiation from the telescope itself would overwhelm its own instrument. So these things are highly sensitive. The JWST has 4 instruments. The near infrared camera or NIRCam, which we saw the image there before of it taking its own selfie, with a spectral range covering from the edge of the visible 0.6 of a micrometer through to the near infrared, which is 5 micrometers. It's also got the near infrared spectrograph or NIRSpec will also perform spectroscopy. I knew I'd get to this point. I've practiced anyway over the same wavelength as the NIRCam. There's also the mid-infrared instrument or the MIRI. It contains both mid-infrared camera and a imaging spectrometer and will measure the mid to long infrared wavelength range from 5 to 27 micrometers. Then lastly, there's a fine guidance sensor and near infrared imager and slitless spectrographer. FGS is used to stabilize the line of sight of the observation during science observations. Measurements by the FGS are used to both control the overall orientation of the spacecraft and to drive the fine steering mirror for image stabilization. So what this means, and this is what it can actually see as compared to an optical telescope. So this is what we're comparing it to, and these images are from the Hubble Space Telescope and a different telescope as well, which I can't remember at this point. Anyway, so compared to the other telescopes, this is what the instruments on board the JWST will be able to see. The images of a distant galaxy in the Hubble Deep Field using advanced cameras for survey. So it's made up of a few different ones here, which is the Wide Field Channel or WFC. The WFC is most utilized channel of the ACS. An example of this is the channel that was this channel was used for sweeps, which is around 16 Canada exoplanets in the galactic core. So that was a Sagittarius window eclipsing extrasolar planet search. That's a mouthful. The near-infrared camera and the multi-object spectrometer, or NICMOS, which is the second image down, you can see just there. The NICMOS is a scientific instrument for infrared astronomy installed on the Hubble Space Telescope, operating from 1997 to 1999 and from 2002 to 2008. The images produced by NICMOS contain data from the infrared part of the light spectrum. Then we get to the infrared array camera, IRAC. The infrared array camera, IRAC, was an infrared camera system on the Spitzer Space Telescope. So that's that last image there. Sorry, the Spitzer, which operated in the mid-infrared spectrum. It was composed of 4 detectors that operated simultaneously at different wavelengths. All 4 were in use until 2009 on May 15, when the Spitzer actually cryostatic ran out of liquid helium, believe it or not. After then, the spacecraft operated in a warm extended mission, in which 2 of the 4 detectors remained functional until the Spitzer was only decommissioned and terminated on the 30th of January 2020. So that's the sorts of things you can get with those types of instruments, and the JWST will be much different to that once again, and we'll look at different spectral wavelengths and things like that. So, all right, this is where I'm going to be quiet for a while and let Aritra speak. And he's going to put together a bit of a presentation, which I'm going to present. So if you bear with me a second, this is going to be a crunchy gear change. So bear with me, guys. I've got several things to do at once. All right, Aritra, off you go.
Can I start?
Sorry. Yes, please. Sorry about that. I'll be quiet.
Yeah, so let's talk about the electromagnetic spectrum. So basically, if we ask any person of common knowledge what light is, so what he's going to answer is basically when we switch on a light bulb, the thing that comes out is light. So that's a very partial answer, to be honest. And the reason why I'm saying that is because the light, as we know, light is made up of light is actually composed of so many different types of what should I say, types of we can say light. Actually, light is composed of different types of light. So the way we differentiate them is basically their frequencies and the wavelengths, because all of these currently on your screen you have a chart right now. So the ones on the left side of your screen, you can see the gaps between 2 subsequent waves is quite small, which is because these waves have a very small frequency. So now as we progress towards the right side of the screen, what we see is the gaps widen, which is because the wavelength is increasing basically. So the thing which I want to convey is, you can see visible light. It's the weight of rainbow, the violet to red spectrum in the center of the screen. So infrared lies between the visible spectrum and the microspectrum. So basically, it has a higher wavelength compared to visible spectrum, but it has a smaller wavelength compared to the microspectrum. So yeah, that's it. Now, if you change the slide for a second. Now, let's talk about infrared radiations in detail, because that's what JWST is going to capture, right? So, on changing the slide, you would be able to see the different types of infrared radiations. So, can we have that for a second? Thank you for that. So here on your screen currently, you can see the basically the different types of infrared spectrum, which I told you lies between the visible and the microspectrums spectra. So basically, JWST is capturing the near infrared to medium. I mean, infrared basically is composed of the 3 different spectra on its own. So basically, you are going from a smaller wavelength to a larger wavelength in infrared as well. So JWST is basically capturing mostly the ones which are lying closer to the visible spectrum. So it's basically an infrared, a close visible infrared spectrum, you can say, in a sense. So yeah, I mean, you can change the slide. Now on this screen you can see the continuous and the absorption spectrum. I'm going to explain them in a bit. So when we consider anything, like let's say any type of body, any type of galaxy, any type of nebula, when we throw light at it, any type of light, we are taking in this special case we are taking visible light. So when we are passing light through any body, some part of the light is getting absorbed while the remaining part is getting reflected. The ones we at the bottom of your screen, you can see there are some black lines on the spectrum. So the spectrum is discontinuous. I mean, it has breaks in between. Why is it happening? Is that the body has absorbed some part of the light which was thrown at it, and it has reflected back the rest of it. So the gaps are the wavelengths which have been absorbed by the body, and the ones which you see the ones which you are able to see on the screen are the ones which are not reflected. I'm sorry, the ones which are not absorbed. I mean, they are reflected by the body. So yeah, that's basically spectrum. Now we can move on to the redshift part. I mean, this is the most important part about JWST. So basically, what happens is when we consider the light coming from the older parts of the universe, like let's say the galaxies formed millions of years ago, what happens is the light increases its wavelength. Now on your screen currently you can see the discontinuous lines, they are moving upwards. What that means is they are moving to the red part of the spectrum. Now the red part is of more wavelength, so it's moving towards the redder part of the spectrum, which is making its wavelength larger. So this is basically redshift, and JWST is able to capture this red what should I say, this change in wavelength with time. So on that basis it can calculate how long I mean what should I say, how many years ago the galaxy was formed, or basically the nebula was formed, the planet was formed, on the basis of the light coming from it. So yeah, that's it.
Really? Wow. Sorry, that's amazing. So based on the shift in the line, they're able to take. Wow. Okay. Yeah. Okay. That's amazing.
I mean, this is a long process. I mean, obviously, it will take millions of years for a wavelength to change. When you're changing the wavelength of the light, and it's basically gravity which is acting on it, Doppler effect acting on it. Yeah, I think I have an animation after this on the slide. Yeah. So this is basically an animation which I took from Wikipedia actually. This is actually a yellow colored body. Now, this is actually Doppler effect. You can say Doppler. I can't explain it in details. What I can say currently is when a body is moving towards you with a great speed, it appears to you. I mean, it appears to you relative. Obviously, it appears to you that the wavelength of the body has decreased. So they are moving toward. The light is basically moving towards the bluer part of the spectrum, and when the body is going away from you, it's I mean, again by the same principle, you can say that it's moving towards the redder part of the spectrum. The wavelength is getting larger. So yeah, I mean, the animation which you are seeing currently is basically a yellow body. When the body is coming closer to you right now, it's green in color, and when it's moving away from you, it's becoming orange. So that's redshift. I mean, the orange part is called redshift. I mean, when the body is going away from you, we know the universe is expanding, right? So I mean, you can say in that way. And
Yeah.
the opposite thing that is happening, I mean, it's becoming green when it's becoming closer. When the body is coming closer, that's called the blue shift.
Okay. Cool. That's incredible. So in other words, we're gonna, because it's moving away from us, we're able to have a look through time, essentially, because the universe is expanding. So we should be able to see through time.
Yeah, that's it. I mean, and that's why I called it a time machine in the previous video.
Yeah. That really explains it very well. And the last slide.
This is basically summing up everything. Webb is currently Webb is currently orbiting L2. So we need time. We need time to cool the instruments. We need time to set up the mirrors. So after that, we can expect a lot of images from it.
Yeah, so with all that, that actually happens towards the to the end of this year. So what that means is, sorry, I've just got to do a crunchy gear change again. I apologise to everyone who's watching at home. This is not going to work. There we go. Sorry about that. All right, so what that means is that it'll take a while for them to actually align the instruments all together, to actually, from those 18 individual telescopes is what it is, to into one solid image, and then we'll be able to see up to 20 years worth of solid science that is going to be available for the JWST. Wow, that is absolutely amazing, and thank you very much for explaining it, because that actually made it very, very clear exactly how all the redshift and that sort of stuff works. So that was amazing. So thank you for that. So yes, we're now reached that important time where, if you have a look over here, guys, you can actually ask your questions. If you have any, is there anything you want to actually explain a little bit better, or anything like that, or us to explain a little bit better, then please hit us up and let us know. Just to let you guys know, while we're waiting for the questions to come in, if there are any, that the JWST is going to, it was a delayed, it was a large expense for all the organisations, but in terms of what we were able to learn about our own universe, is going to be, pardon the pun, astronomical. The things we're going to be learning is going to be quite large, and it's going to be keeping people scratching their heads for a number of years, even after it's been decommissioned, because like all these things, so just give you everyone an example of exactly how much data is coming through. The first initial images that came through were around about 34 terabytes that came through, which is why it has a high capacity, or a high throughput antenna, to actually get all that information back to Earth. So yes, there'll be plenty of times after JWST has been decommissioned after its 20-year lifespan, well, they'll still be searching through data and discovering new things because of this particular telescope. So yeah, very, very interesting.
Thank you very much.
That's all right. Corinna has a question. Hi, Corinna. Thanks very much for joining us. So how long does it take to focus each mirror? Do you have an answer for that?
I guess they're doing it all at once, right? So I guess it was around 4 months, I guess.
Yeah, so what they're looking at is they're looking at the summertime is when they'll start to have all their images and everything aligned. That's optimistically, so that's the American summertime, so the northern hemisphere. So we're looking at around about June, July, maybe August at the absolute latest. What gives me a lot of confidence at the moment is the fact that all the initial images, all the points of light are all together all at once, or very close together, which means that there's not much. What they seem to hint at was there shouldn't be too much alignment to be done to actually get it into the right area. Mark says, thanks very much, Aritra. He actually enjoyed that, a fellow astronomer, and he's very impressed with what you did.
Yeah, actually, we talked this morning. He wished me best of luck, and yeah.
It's good to have Mark on your side. When he was joining me for live streams and stuff like that, it was really, really good. So look, I'm glad he's back in some way, shape or form. So thanks very much for joining us again there, Mark. All right, well, I think that's all the questions and answers. So if there is any more that comes through, guys, remember the chat is there for you to have a chat as well. It's not necessarily to just ask us questions, but it's there for us as well. So as part of the live stream, I thought I'd do one more thing. So yes, I'm going to do. There's a lot of advertisers in this country where they go, but wait, there's one more, and I'm about to do the same thing. So I'm going to take them from the leads of everyone else. So just to let everyone know that. something has been happening in the background, and I'm about to introduce you to the world as one family. So Aritra and I have actually collaborated a lot since our last live stream. So I came up with a series of images to celebrate Australia's collaboration with our international space partners, including the Indian Space Research Organisation, or ISRO. So what was missing from after I created all these photos was how to describe our partnership with our friends in India. So between Australia, so ISRO and the Australian Space Agency. So I needed to come up with a tagline, and you know, quite frankly, all the taglines I had were not great. Fortunately for me, Aritra came to the rescue and actually managed to help me with this one. So I'd like to introduce to you guys the world is a family, with the Australian and Indian flags behind the Aussie with the world as one family written in Sanskrit. The Aussie this Indian Australian Aussie is now available on shop.joshkeegan.com. So yeah, so if you want to go and check that out, go to shop.joshkeegan.com. And very big thank you to Aritra for helping me with that, helping me get across the last little bit there with the line. Very much appreciate it, mate. Appreciation as well. Someone who never watches, however, I need to acknowledge is Rashmi, as someone here that helped me as well to make sure, double checked to make sure the Sanskrit was right. So, in the final image. So yeah, much appreciation to Rashmi. So shout out to her as well. All right, so thank you very much, Aritra, for joining me for this live stream. It's been really, really interesting, and I can't wait to see what the James Webb Space Telescope comes up with next. So thanks very much, mate, for joining me live. So what's the biggest thing? I've got a question for you before we go. Is what's the biggest thing you're looking forward to in the next couple of months once the mirrors start to align?
Anything, to be honest. I mean, it's it sounds flat, but it's anything. Like after after a lot of delays. I mean, even the image which came out today, like the one where there was 18 images. I mean, 18 images of the same star. I mean, even that was pretty. I mean, impressive to me.
Yeah, me too. I mean, and the fact that the NearCam, which is not even designed to actually take a selfie, it actually took a selfie. And apparently there is the rumors are from some of the publications in the United States was even the scientists who were starting to align the mirrors were really surprised that they got that as well. They went, "Oh, okay, we got that." So yeah, they came down from the heavens as well. So. I mean, there's no other way to say it. It came down from space. 1.5 million kilometers away. Let me just say that again. 1.5 million kilometers away in an elliptical orbit at L2. So, yeah, that's just absolutely amazing. So, the biggest thing I'm looking forward to at this particular point in time is I'm very much on your side, Aritra, is I'm looking forward to anything coming out of this. It's just going to be mind-blowing. But what I'm looking forward to is once this is decommissioned, well, like once we discover all these things and how much longer when people comb through old data from JWST that will still be discovering new things, even though there might be a replacement and all that sort of stuff. So it's just going to be a fantastic 20 years, and I just can't wait. 22 to 42. So hopefully, mate, we'll get to catch up annually and talk about JWST and what it's found. All right, mate. So look, I'll leave you here, and look, I'll go through the outro with everyone. So just say again, Aritra, thanks very much for joining me, and I'll just. Oh, there we are. There's the main screen, and it's just me. All right, so if you guys like this live stream, please remember to head on over and subscribe to my YouTube channel. When you are subscribing, you also remember to hit that notification bell. So every time I upload a video, you get to know about it, and you get to know about it first. And while you're there, if there's a video you've enjoyed, if this is a video you liked or there's another video you've enjoyed, please like and make a comment. This way it lets YouTube know to share my channel with more people so that they can learn more about the space down under, just like you guys. All right. So thanks very much for watching, and remember, stay caffeinated.